lecture or this chapter or the last chapter in this course is about benzene and aromaticity. And of course, the first thing we are going to discuss is simply the naming of the benzene and the nomenclature, what we are going to use in this chapter. As you can see here in this slide, we have the benzene as such, we call it benzene. Sometimes, as such, this is the whole chapter is about this structure. This is called the benzene. Now, sometimes some substituents, when they are attached to the benzene, they change the name and it becomes another name. For example, if we have a methyl at the benzene, we don't call it methyl benzene anymore, we just call it toluene. This is actually a common name, but it is yet approved by IUPAC. So from now on, we use it as toluene, or we name it as toluene. So whenever we have a methyl attached to the benzene, we name it toluene. The same thing here similarly. If we have two methyls, we call it xylene. If we have two benzene rings together, we call it naphthalene, and so on and so forth. These are examples of the aromatic compounds which we are going to discuss in this chapter. All right. Now, there are some common names, as I said, which simply, or some substituents, when they are attached to the benzene, they change the name of the compound. For example, like the toluene. Another example here, like carboxylic acid. If we have carboxylic acid attached to the benzene, we call it then benzoic acid. So it's not anymore or any longer benzene system. Do you follow me, guys? Is there any question so far? Is there any question?
No, doctor.
Perfect.
Doctor?
Yes, please.
Benzene should attach just for one molecule?
The benzene, as I said, the benzene is this benzene. This is benzene. Now, when it is attached to anything or anything attached to this benzene, then it's substituted benzene. Do you follow me? Some substituents, like this substituent, when it is attached to the benzene, we just call it benzoic acid. Change the name. It becomes benzoic acid. If there is a methyl at the benzene system, we call it toluene. So you have to remember this. This is toluene if a methyl attached to the benzene. If, for example, like the examples that you have it in here, for example, if aldehyde is there, then we call it benzaldehyde. So we call this benzaldehyde. So this is simply these names, as I said. These names are common names, but yet they are approved by IUPAC. Got the point?
لا أقصد إنه يصير يرتبط بأكثر من شيء.
Yes, of course. We will come to this. We'll come to this in the next slide. Definitely, it can be attached actually to 6 substituents, as you can see. It's not just one. But as I said, these monosubstituted or these monosubstituents, when they attach to the benzene, they change the name. It becomes something. Here, carboxylic acid, as I said, becoming benzoic acid, toluene, benzaldehyde. You see the table in this slide here? You must know it. You must know all of these common names approved by IUPAC. Got it? Is that clear, guys?
Yes, doctor.
All right. Now let's name it by IUPAC. Now, when we have substituents which don't change the name of the benzene system. For example, any other substituent such as halogens or other substituents, they are nitro, something like that, they don't change the name. For example, here, if we have bromine here, if we have monosubstituent which don't change the name, then we just name the substituent in this case, which is bromo, and then we add the benzene. So this is for monosubstituent benzene. If you have a nitro, for example, then we call it nitro, then benzene. No need for any numbering in this case because it's monosubstituent. If we have iodine, for example, we call it iodo benzene. Do you follow me? So this is the rule for monosubstituent benzene. For disubstituent benzene, imagine, for example, we have two bromine atoms attached to the benzene system. In this case, we will have three possibilities for the two bromine to be attached to the benzene system. Let me just erase this. Maybe this is more clear in here, or this size at least. If we have for disubstituent or disubstituted benzene, let's say, for disubstituted benzene, we have three possibilities for the two substituents to be at the benzene system. Either to be beside each other or at 3 carbons distance from each other or at 4 carbon distance from each other. In this case, we simply have to name the two substituents and then we have to number the system. Of course, the number here will be 1, 2. The number here will be 1, 2, 3. The number in here will be 1, 2, 3, 4. So the name will be here 1, 2 dibromobenzene. In this case will be 1, 3 dibromobenzene. And in this case will be 1, 4 dibromobenzene. Do you follow me? So this is usual as or similar to the naming of disubstituted or disubstituent when we have it at a cycloalkane or cycloalkene, whatever. So we just name the two substituents and then simply designate their location at the cyclic system. Specifically for benzene, we may use, instead of saying 1, 2, we may say ortho, and we simply use the first term here. The 1, 2 can be used, or we can use ortho instead of it. 1, 3 we can say meta, and 1, 4 is para. And instead of writing meta, ortho, para, we may say simply O, 1, 2 dibromobenzene. Here, M, the first letter only. I'm so sorry. Instead of writing 1, 2, we just say ortho dibromobenzene. We just say here meta dibromobenzene. In this case, we just say para dibromobenzene. Do you follow me? In the case of benzene, when we have two substituents, we either use the numbers to designate the location of the substituents, or we use just O for 1, 2, M for 1, 3, P for 1, 4. P stands for para, M stands for meta, O stands for ortho. Is that clear?
Yes, Doctor.
Is there any question about it? Is there any question?
دكتور إذا من الجانب الثاني.
It's the same. Because if this case or that case, it's the same. Because always we look for the lowest number. Do you remember that?
Yes, yes.
See, if it is here, for example, suppose we have BR. This is exactly like this one. Because it's 1, 3 or it's meta. Do you follow me? But remember this word, we use ortho, meta, para only for, in the case of two substituents, فقط. Never use ortho, meta, para if you have more than 2. If you have more than 2, stop. Never use it. Just use numbers. Got the point? Please take this as a note and write it down, because you're gonna use it more again and again in the future. Clear? Is that clear?
Yes, doctor.
Okay, perfect. Now let's move ahead and for the next slide now. Now, before talking about this, I'm just going to continue first for 3 substituents, and then I'm going back to the use of phenyl. Now, for 3 substituents and more, for 3 substituents and more, we just use. Actually, there are 2 cases here, or we use the lowest set of numbers. This is simply the rule. That's exactly the same rule when we were talking about cycloalkane, if you remember. We always look for the lowest set of numbers and we take it as our number. For example, here, what would be the name of this compound? What's the name of this compound? What do you think?
1 bromo,
Mm-hmm.
3, 4 dichloro, benzene.
1 bromo, 3, 4
4
dichloro benzene. Now the question is this name in agreement with this rule or not? So let's just say it again here. What are the set of numbers you given for this name?
No, we can start with Cl. 1, 2 Cl.
Right, but let me just finish this. Just to discuss your possibilities. You give the set of numbers here 1, 3, and 4, isn't it? Right?
Yes.
Now, what's the rule here? We have to use the lowest set of numbers. Is there any other possibility to get lower set of number than this? Of course, yes. If you start naming from here or numbering from here, you will get 1, 2, 3, 4. We're gonna get 1, 2, 4. Do you follow me? Now, which set is less or lowest set of number? The first set or the second set? Or let's say A set or B set. Which set is the lowest set of numbers?
B.
Akid. So B is the lowest, therefore this B is correct, and this is not true. But we say 4 bromo then, and then 1, 2 dichloro benzene. Get the point, guys? Is that clear? Come again, please. Of course not. Because as I said just a minute before, never ever use ortho or meta or para in case of more than 2 substituents. Got it?
Yes.
So never use it. Ortho, meta, para only used or can be used instead of numbers for the case of 2 substituents. When we have more than 2, khalas, done. We only use numbers. So that's why this is the name of the compound. So as you can see, this name is correct, this name is wrong. We should not use this numbering. The first numbering is wrong, the second number is true because the second numbers or numbering, it includes the lowest set of numbers. Right. Okay, so far, is that clear, guys? Yes, go ahead.
السبستيوانتس هذه تكون بدال الاتش في
Yes, exactly. We'll come to the chemical structure a little bit yani after a few minutes from now, but for the time being, we're just talking about the naming. So it's obvious now, if you have a substituent here, then there is no hydrogen in here, as you'll see now in the next slides, just a few minutes from now. Now, the other point here, when we have the benzene as such, or when we should use the benzene as a substituent, then what should we do? For example here, suppose you have CH3, CH2, CH, attached to CH2, 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 CH3. Now in this case, as you can see, we have two systems. We have cyclic system, and then we have long chain system. Now in this case, we have to decide which one is which. Now, generally speaking, whenever we have two systems like these, we always use the parent name as the longest, the chain, or simply the system which includes or which contains more numbers of carbons. In the long chain here, we have 7 carbons, as you can see. In the cyclic system, we have 6 carbons. So it is obvious that this is our parent name. Clear? In this case, this cyclic system will be like substituent. And to name the benzene as a substituent, we use it, or we name it as phenyl. So whenever you need to name the benzene system as a substituent, not as a parent name, then we must use the term here of phenyl. So in this case, the name here will be 3-phenyl-heptane. Is that clear, guys? Do you follow me?
Yes, Doctor.
So,
Doctor, سمحت أعيد تعيد.
yeah. Now, as you can see here, for this example, as you can see, we have long chain and we have cyclic system. The cyclic system, the benzene, it contains 6 carbons, isn't it? The long chain contains 7 carbons. We must consider always the system which includes more number of carbons. طبعا, this case here, the long chain will be our parent name. So this here, the benzene system, becomes a substituent like to the long chain. Whenever we need to consider the benzene system as a substituent, we name it as phenyl, not any longer as benzene. Because always there is a rule in the APAC, we cannot have, or we must not have more than one parent name. So in any compound, there is only one parent name, and the rest are just substituents to or over this parent name. So in here, either this to be the parent name or this to be the parent name. What's the rule? Always the longer number, or the system which contains more number of carbons. Here we have 7, then this is the parent name. Here we have 6, then this must now be considered as substituent. To be considered as a substituent, we name it as phenyl. That's why we have to name the compound as 3-phenyl-heptane. Got it?
Yes.
All right? Yes, please.
إذا كانوا 6 و6 من وين نبدأ نرقم؟
Generally speaking, if we have benzene and cyclic system, then the benzene should be the parent name in this case. Actually, both are fine actually by the APAC, but in this case, for example, here, CH2, CH3, for example, CH2, CH2, CH3, you simply you can consider here this as a parent name or this as a parent name. what's the easiest for you? The easiest for you maybe to consider this as a parent name, just to say it's 3-phenyl hexane. Or if you want, you may consider this as a substituent too. It works fine, you know. It's actually the rule in here, what's easier for you. Both are fine if they are containing the same number of carbons. Got it?
Yes.
Alright. Now, this is regarding the phenyl, and generally speaking, we sometimes use the terminology or the abbreviation of pH to indicate a phenyl. Yani, whenever you see a pH in the structure from now on, you should simply know that there is a benzene system there, or it's a substituent of benzene system. For example, like this example in here, it's not there actually, but anyway, sometimes we may write phenyl in this case here. Now, sometimes, or another substituent which is related to the benzene system, which is simply this case here. Whenever we want, or whenever we need to consider this system, this system, as a substituent, when we want to consider this as a substituent, we name it benzyl. So you can see here, when we have a benzene system attached to one carbon only, and all of this system is attached to a longer chain. In this case, we consider this, when we need to consider this as a substituent, then we call it benzyl. Do you follow me? Let me just give you an example when or what example we may consider it. For example, here CH3, CH2, CH2, CH, CH2, 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 1, 2, 3, 4, 5, 6, 7, CH3. As you can see here, what's the longest chain of carbon atoms in this example? How many carbon it contains? How many carbons it contains?
8 carbons.
Exactly. This is the longest chain, which contains 8 carbons. What does that mean? It means all of this, you can see here, all of this, it should be a substituent on the 8 carbons, or on the long chain. Now the name of this here, you can see the CH2 and the benzene together, we call it benzyl. بالتالي, the correct name here will be 4-benzyl octane. That's it. Do you follow me? 4-benzyl octane in this case. We call it as benzyl in this case. Clear? Is that clear, guys? Is there any question? Now, check here this slide here. This compound 2,5-diphenyl. Huh? Is there a question? All right. What's the correct name of this compound in this case here? What do you think? Here, let's just take another example just for the nomenclature. The same example what you have it in here. All right. So, what do you think should be the name of this compound, or what's the rule here? What's the rule whenever we have more than 2 substituents at the benzene system? What should be the rule here? What's the rule?
Will be 1 ethyl.
I know, but what's the rule behind it? Whenever we have more than 2 substituents, what's the rule?
Use the lowest number of.
Lowest group of numbers, not just lowest number, lowest group of numbers. Do you follow me? Which means the lowest group of numbers here, we must start from here, 1, 2, 3, 4. There is no lower set of numbers compared to this group of numbers. So it will be 1 ethyl, then what? 1 ethyl, then
2 and 4.
2, 4 dinitro benzene. Do you follow me? It's actually straightforward for the epoch nomenclature. There shouldn't be any ambiguity actually in the numbering. All right. Now let's talk about the structure of the benzene, and we are just going to go through some sort of, some of historical aspects of the structure of the benzene. As you know, the structure of benzene is this structure. It says chemical structure of benzene. And the molecular formula of benzene is C6H6. As you can see here, we have 3 double bonds inside the cyclic system, and each carbon here, each carbon is sp2 hybridized 1, right? Because here, every carbon here is sp2, 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 and so on. You follow me? So this is the structure of the benzene. There is something special about this structure which we need to consider now and which we need to discuss. The first aspect, if we write this structure, what does that mean? It means that we have alternation of double and single bonds, as you can see. We have double, then single, double and single. Yani, regarding the carbon-carbon bonds, we have 3 carbon-carbon single bonds, and we have 3 carbon-carbon double bonds. Is it true? Isn't it?
Yes, it does.
Right. Now, which means actually we may simply, or we can simply have like the 2 bromines, as you can see it in here, or it's, we will come with it. Actually, in this case here, if we consider it like that, which means we have like 2 systems, like 2 bond length in this case, which is not true, because of course the single bond length is different than the carbon double bond bond length. Which one is shorter? Which one is longer? Carbon-carbon bond or carbon double bond carbon? Which one is longer?
It's carbon-carbon.
Carbon-carbon is longer. This is longer bond. Then as the number of bonds increases, the attraction forces between the 2 nuclei increases, and therefore these 2 nuclei becoming closer to each other, or the distance becoming shorter. So, which means if this is true, if this is the representation or the correct representation of the benzene system, we should find 2 bond length of the inside the benzene system, which is not true. We didn't find it. What we found that all carbon-carbon bond length are the same, identical. Do you follow me? Which then will lead to the conclusion that this is not really the correct structure which simply can represent the actual behavior of the benzene. The correct, or I'm just going to remove the hydrogens for the time being. The correct representation of the benzene system must be actually what we call it resonance structure of the benzene system. In this case, here, this as such cannot simply explain why all carbon-carbon bond lengths are the same. We must have another resonance structure which is simply then, in this case, the other resonance structure, this goes here, this goes there, and this goes there. And then what we're gonna get, we are going to get this. Do you see the difference? Wherever we have carbon double bond carbon, here becomes carbon single bond carbon. Wherever we have carbon carbon single bond, it becomes carbon double bond carbon. So this is the actual, this is, let's say, the most acceptable structure which can explain then the behavior of the benzene. Do you follow me? So benzene, let's say, just to make the story short, benzene present in two resonance structures. Let's say two identical and equivalent resonance structures, and the actual hybrid or the actual representation can be, sometimes we may represent the benzene this way. Instead of writing the double bonds, we just make it like a cycle inside the ring, just to show or to mention that this structure simply is actually a hybrid of two resonance structures, which are these two resonance structures. But from now on, actually, just for practical use, in principle, we may write the structure is benzene is this or that, just for simplicity and to make things easier for us. But even if we write the structure of the benzene as this or that, we must always remember that benzene, the actual structure of the benzene, is a combination of two equivalent resonance structures, what will make actually the real behavior of the benzene system. Clear, guys, so far?
Yes.
All right, and that's actually what the benzene system has special stability. As you can see in this slide, in the slide here, where you have it, we compared the delta H of hydrogenation of three systems. We compared the delta H of hydrogenation of cyclohexene when we have one double bond inside the system, and we hydrogenated in presence, for example, of palladium, we're gonna get cyclohexane. And the same thing if we have two double bonds, when we hydrogenate them, we should expect to get cyclohexene. And when we have benzene system, we should, again, if we hydrogenate it under very special conditions, under very high temperature and pressure, we should get simply cyclohexene in all cases. This reaction or these reactions are exothermic reaction, so we are going to get heat every time we do hydrogenation. And the heat of hydrogenation depends on the number of the double bonds. In the first one, when we have only one double bond, the delta H of hydrogenation was, how much was it? It was 118 kilojoule. 118 kilojoule. Which means here, the delta H of hydrogenation of this here should be the double of that, isn't it? Because here, for each double bond, we will get the delta H here at 118 kilojoule. If we have two double bonds, we should expect to get the delta H to be 2 times this. But what we got actually is 230. This is what we got. This is experimental. Expected, we should expect to get 118 times 2, which means we should expect to get 236, which is almost the same approximately the same. Yani, we should conclude that to have these two double bonds with these two positions, we should expect it to be a little bit more stable than what we should expect. But when we done the hydrogenation of the benzene, we got the hydrogenation of the benzene to be 200. First of all, expected hydrogenation of the delta H of the hydrogenation of the benzene, how much should be? What's the expected delta H of this reaction? You tell me, guys. Why al-zuhur? Why should be? It should be 3 times 118, not 4. You will follow me? If we have 3 double bonds here, so it should be 3 times 118, which is equals to how much, Jama'ah? It's, if you multiply, it will be 354, right? I guess so. Should be 354 approximately. 356. No, it's 354. Yeah. Right? Yeah, 354. Now what we got is what? How much? 230. You see, what we found is the delta H is 250, which means that there is the benzene system has very special stability, and this stability is around 150 kilojoule per mole. So it has, which is approximately the difference between no, it's around how much? 100 kilojoule the difference, right? We got 230 is supposed to be 102. This is 230. So approximately the difference is around 120, regardless of the difference. But anyway, it's around 124 kilojoule. Do you follow me? So, to make the story short, the summary of this slide just showing that the benzene has extra stability than expected with approximately 124 kilojoule, which is a huge amount of energy. Now the question is why? Why the benzene is so much stable and it has special stability? This is actually due to what we call it, if we just continue writing, this is due to something special about benzene, which is simply called aromaticity, due to aromaticity. And what's the aromaticity? Or this is actually what we are going to discuss it right now. So benzene has special property, which we call it aromatic or aromaticity. That aromaticity makes special stability or make it very much stable compared to expected behavior. Do you follow me? Now what's aromaticity and why benzene that much stable compared to what we are expecting? If we come back to the original structure of the benzene system, you will see it, as I said, in here each carbon is attached to a hydrogen, and we have 3 double bonds inside the system, and each carbon is sp2 hybridized carbon, isn't it? Which means that we have this bond is sp2, sp2, sp2. Do you follow me? Each carbon makes sp2 hybridization, therefore it makes a bond sp2, sp2 here, sp2s, sp2, sp2, and so on. Now, the remaining on each carbon, there is a p orbital. I'm just going to show you using the model just to understand the special aromaticity of the benzene system. Just show me the camera. Let me see just want to see myself. Don't know why I don't see. Okay, let me see here. Can you see, guys? Do you see the model now? See it? Okay. Now, as you can see here, these red colors, forget them now for the time being. Now here you can see the black ones are each carbon, and each carbon is sp2. I'm just going to remove these red colors for the time being because I don't have model to show you orbitals. Do you follow me? أعطيني بس واحد بابا كمان أحمر. Oops. Just going to show you this for a minute. Now you can see, right? You see this is the benzene system. Do you follow me? It's a planar system, and these hydrogens are out of the system. You can see it like here, right? Now each carbon here, it is sp2 hybridized. What does that mean, sp2 hybridized? There is p orbital on each carbon because we used s and 2p for bonding or for making bonds, and therefore we have now p orbital on each, and we know that p orbital we have two loops above the plane and below the plane. Therefore we're gonna just put it like this just to show you now the bonding and the chemical bonding of the benzene system and why this special structure make it very special stable. It has extra stability as we have proven in the previous slide. Now you see, basically each p orbital here, which as we said, the p orbital has one loop above the plane and one loop below the plane. You see now the electrons, each p orbital has one electron, one electron, one electron, one electron, one electron. Now there is a special option in here for these electrons. Instead of making a bond between the two adjacent p orbitals together, they can simply move all around the system in a circular motion, because like we have a track for moving of these electrons, for these p electrons. Do you follow me? So the electrons actually making in this special system, in this special structure, electrons are making like a cloud of electrons moving above the plane and below the plane, because as we said, p orbital are two loops or containing two loops. One loop is above the plane and one loop is below the plane. This here, this chemical structure or this freedom of the movement of electrons around the cyclic system, that's actually what makes the benzene system has a unique structure and a unique stability, which we call it aromaticity. So the aromaticity is the ability of electrons to move or in a circular motion or around a cyclic system freely without any boundaries. That's actually simply the aromaticity, and that's the reason for stability of the benzene system. Can you see, guys? Is there any question about the structure, about this chemical behavior and this chemical structure of the benzene? Is there any question?
It is clear.
All right, perfect. So that's actually the reason now, and that's why now it's very important for you from now on to remember this, that certain structure, when they have the benzene system, we should expect to have special stability. Remember that. Any structure mimicking the behavior or similar to the structure of the benzene should behave or should show special stability. And therefore, it should simply be accompanied with special chemistry. And therefore, remember my words, the first chapter where you are going to study in Organic 2 will be the reactions of benzene, which is simply special type of reactions, which we will call them electrophilic aromatic substitution, rather than just the behavior of the benzene system. of the alkene system. You follow me? Now, just to show you, just to emphasize on this. In principle, the benzene system in here, you see, the benzene system, it includes 3 double bonds, right? And we did actually study the behavior, or we did study simply the reactions of alkenes, because you may consider this, or you may assume that this is like alkene behavior, which is totally not. Actually, in the chapter in Organic 2, you are going to study what we call it electrophilic, aromatic, substitution reactions, which is special reactions for benzene system or aromatic system. This is actually the first chapter which you are going to study it actually in the Organic 2. Just going to get back to the slides in order just to can you see the presentation? I think the presentation stopped. Yeah, I'm just going to show you again the presentation. I think I need to open it up. Anyway, you just simply follow the presentations, because I don't have now the ability to show you. It seems that something wrong with it, because sometimes it goes strangely. I'm just going to try it again. Let me see if I'm going to succeed to do so. Okay, unfortunately I can't, but anyway, I'm just going to continue showing you. I'm just continue to follow the slides. Please follow the slides while I'm just talking about it. I'm just going to talk about the aromaticity and how we can simply consider if a system is aromatic or not. Now, what makes benzene system special and has special stability and special chemistry? It's actually what we call it the aromaticity. Now, how can we know that if a system behaves similar to the behavior of benzene or not? This is called aromaticity or aromatic system and Haeckel rules. Haeckel's rule. The Haeckel rule is stated like that: for any system to behave aromatic, it must contain the following, all of the following. First, it must be cyclic system. The first condition must be cyclic. So the system must be cyclic system. Second, must be planar. All carbon atoms or all atoms involved in the aromaticity or in the circulation of electrons must be planar on the same system. First. And second, they must be planar. And third, they must contain 4n plus 2 by electrons. This is a very important rule here, which is simply we must always take it into consideration. For example, the benzene system here, you can see the conditions here. First of all, it is cyclic. So it is true. Second condition, it is planar. Of course, it's true because all these atoms, all carbon atoms are on the same plane. The third, how many electrons we have in the in the cyclic system, in the benzene system? How many electrons we have? How many electrons we have in the benzene system? Hello? Any answer? How many?
3 or 6.
There are 6 electrons. 2, 4, 6. Each pi bond here contains 2. So there are 6 electrons. Are the 6 electrons inconsistent with this rule? Yes, because here the number of electrons allowed to be in the system must be one of these numbers, 4n plus 2, where n here can be 0, can be 1, can be 2, 3, 4, whatsoever. So let's see what are the number of pi electrons allowed to be within the cyclic system. If we apply 0 here, it will be the number of electrons by electrons should be starting from 2, 6, 10, 14, and so on. So any of these numbers, when we have these pi electrons inside the system, then we can consider the system as aromatic system. Clear, guys? Is that clear?
Clear, Doctor.
So that's actually the reason why the cyclic system. Now let's see, do we have other systems which behave similarly, which behave like benzene system or not? If they have to behave, or if we have to consider them as aromatic, they must contain the same rules here. For example, let's see this compound, which this is one example of heterocyclic aromatic system, which we call it pyrrole. And the pyrrole in here, you can see here we have a nitrogen here instead of one of the carbon, or before, sorry. Now, here, for example, we have also pyridine. The pyridine here, this is called pyridine. The pyridine is similar to the benzene. This system, we call it aromatic, or both systems, we call it aromatic. Why? Because simply this system is cyclic, planar, all atoms involved are sp2, and number of electrons, 6 electrons. Here we have the same. We have a cyclic system, we have planar system, all atoms have sp2 hybridized, and therefore the number of electrons here involved are 6 electrons, because simply the nitrogen in here will use here, how many electrons, pi electrons here for the pyrrole? How many? Do you see, guys? Hello?
4 electrons.
It is 6 electrons, because see here we have 2 electrons from this double bond, 2 electrons from here, and then we have these 2. These 2 are part of the aromatic systems. So therefore this compound we consider it to be aromatic. This here also we consider to be aromatic, because here there are 6 electrons coming from the pi electrons from here. Do you follow me? You follow me, guys?
Yes, Doctor. المفروض 8.
When? Where? In which here? In the pyridine?
لأنه بعدل النيتروجين من هيلهم فيه.
would you please just repeat the question?
ما المفروض يكون عندها 8 إلكترون؟
Which one? The pyridine or the pyrrole? Which one you are talking about?
البريدين.
Pyridine. Why it should be 8?
لأن النيتروجين عندها لون بيربعة.
You are absolutely right. You are perfect. That's true. But this here, this pi electrons here is not included in the system. It is away from the system. Do you follow me? Specifically this here, this lone pair, in this example, it's not part of the aromatic electrons. So that's why here, the pi electrons which are involved are 6 only. That's why it is aromatic. If these 2 electrons, for any reason, if they are part of the system, it will not be any more aromatic because the number of electrons here will be 8, not 6. Do you follow me?
دكتور كيف نعرف السكر؟
Yeah, this is the point here. Just a second here. It's the knowledge of heterocyclic, that's it. It's not a big deal actually. These are 2 examples here. If it is similar to the benzene, this lone pair will be not part of the aromatic. If this is a 5 cyclic member ring, the lone pair here will be part of the aromatic. That's it. We just know that pyridine and pyrrole are aromatic. Or they simply have special aromaticity, which means this lone pair is not part of the system. Alright, let me just give you another example, just to show you. We'll come back to this later on. It's okay. Now let's just take another example here, for example. Is this system aromatic or not aromatic? This is actually 1, 3, 5, 7 tetra octatriene. How many? Is it aromatic or not aromatic?
Not, doctor.
Why it's not aromatic?
Because it has 8 electrons.
Absolutely. So this is not aromatic. So what does that mean? Is benzene aromatic or not aromatic?
Aromatic.
Perfect. So what? What does that mean? What we need this classification for? That's actually the major question here, the $1 million question. What we needed, this is aromatic, which is true, because it simply fulfills all requirements. This is not aromatic. So what does that mean? Can anyone tell examples and you can see it? Is this species, this is carbocation, is this species aromatic or not aromatic? What do you think?
Aromatic.
Why? This species, this carbocation is aromatic because it is first cyclic and must be cyclic. It's planar, and all atoms are sp2. You follow me? Then the number of pi electrons, how many pi electrons? It has 2 electrons only. You follow me? So which means the 2 electrons is part of the Haeckel's rule. Therefore, this here fulfill the requirement of aromaticity. So we call this aromatic compound. You follow me? Now, let me to give you more examples.
دكتور.
Yes, please. Yes, please.
اللي عوضنا رقم كم يعني؟
What?
هذا السؤال قبل n كم نحطها في القانون؟
Any n, it's just the number of pi electrons. If you wanna memorize it, memorize. If you don't want to memorize, use the rule. It's either you say 4n plus 2 is the number of pi electrons must be, where n here is equal 0, 1, 2, 3, 4, 5 until infinity, and then you apply. Or you may say the number of pi electrons must be 2, 6, 10, 14, and so on. The pi electrons. Do you follow me? That's why we consider it aromatic. Do you follow me?
يعني نعرف أن اثنين هنا تساوي صح؟
In this case, بس كملي.
دكتور
Yes.
أنا فاهمة اللي هو شوفوا يا جماعة، فإحنا نحط إنه 2 أو 6 أو 4 نحسب عدد الإلكترونات. إذا أعطانا 2 أو 6 أو 4 أو لا 4 2 أو 6 أو 10 أو إلى آخره يعتبر أروماتيك. إذا حسبنا عدد الإلكترونات طلع لنا 5 مثلا أو 7.
أي رقم آخر, any other numbers, it's not aromatic.
It is not aromatic.
Is this your question? Now let's take this another example. It becomes more clear. This example here, is this aromatic or not aromatic? This species here, is this aromatic or not aromatic? Let's see the conditions. Let's see the requirement. Is this structure cyclic? Yes, it is cyclic. Is it planar? Yes, it is planar. Is it all atoms are sp2 hybridized? Yes, all are sp2 hybridized. Because always, whenever we have charge, it will be also sp2 hybridized. How many pi electrons we have in this system? The one who are asking, how many pi electrons we have in this system?
3.
Why 3? It's 4. 2 electrons in this pi electrons and 2 here, because here these are 2. Any negative charge is 2 here. So the total here is 4 electrons. Do you follow me?
Yes.
So is this aromatic or not aromatic?
Not.
Why? Because the number of pi electrons are not fulfilling the Huckel's rule. So this is not aromatic. That's it. Do you follow me? Yani don't make it complicated. It's very easy. You have conditions. These conditions must be fulfilled before we consider it as aromatic. If any of these conditions is not fulfilled, then it's totally not aromatic. That's it. Got it?
Yes.
Okay, let me just give you more example. Take more example. Take this anion as an example here. Is this species aromatic or not aromatic? Take 1 minute to think about it and then let me know. What do you think?
Aromatic.
First of all, let's together make it. Now, what are the conditions? Is it cyclic?
Yes.
Cyclic. Is it is it planar? Yes, it's planar actually, the cyclic system here. It's planar. Second, all carbons or all atoms involved are sp2 hybridized? Yes. How many electrons we have? We have 6. 2, 4, and 2 are 6 here. So we have 6 pi electrons. Therefore, this is definitely aromatic system. Sometimes we may have also a combined system or fused aromatic, what we call it. For example, the naphthalene here. Let's talk about the naphthalene. This system also is aromatic. This is aromatic system 2. Why the naphthalene is aromatic system? Because again, the conditions are all applied or fulfilled. The pi electrons in here, how many pi electrons we have in this system? How many pi electrons we have in this system? The total pi electrons we have it in this system. How many?
10.
10. And that 10, it's simply part of the aromatic system. Do you follow me? Clear? Now, for example, if you have this system also Now, is this system aromatic as a whole? Is this system as a whole, is it aromatic or not aromatic? What do you think?
Not.
It's not aromatic. ليه؟ لأن total number of electrons, of course, يعني part of it is aromatic. Benzene alone is aromatic. Like as a whole, is not aromatic because it's not aromatic because the total number of electrons are 8 electrons. Do you follow me? Now, does anyone can understand or can explain this hydrogen? One of these hydrogen has very high acidity. Can anyone explain to me why this hydrogen has very high acidity, unusual acidity? Would you explain it to me?